Hey there, science explorers! Have you ever wondered what keeps you grounded on Earth? Why doesn't our planet just drift away into the vastness of space? What causes the moon to orbit our planet? The answer lies in a fundamental force of nature: gravitation. Gravitation is an invisible force that attracts any two objects with mass towards each other. It's what keeps your feet firmly planted on the ground, preventing you from floating away. It's the force responsible for the majestic dance of planets around the sun and the rhythmic ebb and flow of ocean tides. From the smallest particles to the largest celestial bodies, gravitation plays a crucial role in shaping the universe as we know it. In this exploration, we'll delve into the fascinating world of gravitation, unraveling its mysteries and understanding its profound impact on our everyday lives. So buckle up and get ready for a cosmic adventure as we demystify the science behind this fundamental force. Get ready to unlock the secrets of gravitation. Our journey into the world of gravitation begins with a simple yet profound observation: an apple falling from a tree. This seemingly ordinary event sparked a scientific revolution, thanks to the genius of Sir Isaac Newton. Legend has it that a young Isaac Newton, while sitting under an apple tree, was struck by a falling apple. This sparked a question in his mind. Why did the apple fall straight down and not sideways or even upwards? This simple question led Newton to one of the most groundbreaking discoveries in the history of science: the law of universal gravitation. Newton realized that there must be a force pulling the apple towards the Earth, and this force, he reasoned, must be universal, affecting all objects in the cosmos. Newton's apple story, though possibly apocryphal, beautifully illustrates how simple observations can lead to profound scientific breakthroughs. It highlights the power of curiosity and the impact a single question can have on our understanding of the universe. Newton didn't just observe the falling apple, he went on to quantify the force responsible for it. He proposed that every object in the universe attracts every other object with a force that is 1. Proportional to the product of their masses. The more massive the objects, the stronger the gravitational attraction between them. Think of a bowling ball and a tennis ball. The bowling ball has more mass, so it has a stronger gravitational pull. 2. Inversely proportional to the square of the distance between their centers. The farther apart the objects, the weaker the gravitational force between them. Imagine holding two magnets. They pull towards each other strongly when they're close. As you move them apart, the pull gets weaker. These principles are elegantly encapsulated in Newton's law of universal gravitation, which can be expressed mathematically as: this formula, though seemingly complex, beautifully captures the essence of gravitation, providing a mathematical framework to calculate the gravitational force between any two objects in the universe. Let's break down Newton's law of universal gravitation formula to understand its components. F represents the force of gravity, the invisible pull between objects. G is the gravitational constant, a fundamental constant in nature that determines the strength of the gravitational force. M1 and M2 represent the masses of the two objects. Mass is a measure of how much matter an object contains. R is the distance between the centers of the two objects. This formula tells us that the force of gravity, F, is directly proportional to the product of the masses, M1 times M2, of the two objects, and inversely proportional to the square of the distance, R squared, between their centers. In simpler terms, the more massive the objects, the stronger the gravitational attraction between them. The farther apart they are, the weaker the gravitational force. Section 5. Mass versus weight. Why we weigh less on the moon. Mass and weight are often confused, but they are different. Mass measures an object's resistance to acceleration. It's how much matter an object contains. Your mass stays the same everywhere. Weight is the force due to gravity. It depends on mass and gravity's strength. On the moon, gravity is weaker, so you weigh less there. But your mass remains the same. That's why astronauts can leap on the moon. Section 6. The Earth's pull. Understanding gravitational acceleration. We know that objects fall to the ground due to Earth's gravity. But have you ever wondered why objects of different masses fall at the same rate in a vacuum? The answer lies in gravitational acceleration. Gravitational acceleration is the acceleration that an object experiences due to the force of gravity. Near the Earth's surface, this acceleration is approximately 9.8 meters per second squared. This means that for every second an object falls, its speed increases by 9.8 meters per second. The remarkable thing about gravitational acceleration is that it's constant for all objects near the Earth's surface, regardless of their mass. This means that a feather and a bowling ball, if dropped in a vacuum where there's no air resistance, would fall at the same rate and hit the ground simultaneously. This concept of gravitational acceleration is crucial for understanding how objects move under the influence of gravity. Section 7. Falling with style. How gravity affects falling objects. The way objects fall is fascinating. In a vacuum, where there's no air resistance, all objects fall at the same rate, regardless of their mass or shape. This is because the force of gravity acts equally on all parts of an object, causing it to accelerate uniformly. However, in the real world, air resistance plays a significant role in how objects fall. Air resistance is the frictional force that opposes the motion of objects through the air. The amount of air resistance an object experiences depends on its shape, size, and speed. For example, a feather falls slowly because its large surface area creates a lot of air resistance. A bowling ball, on the other hand, falls quickly because its compact shape minimizes air resistance. Despite the effects of air resistance, the fundamental principle remains: gravity pulls on all objects, causing them to accelerate towards the center of the Earth. Section 8. Beyond the apple, gravitation's role in our world and beyond. Gravitation's influence extends far beyond falling apples and our planet. It's the invisible force that governs the motion of celestial bodies, shapes galaxies, and influences the very fabric of space-time. Here are just a few examples of gravitation's profound impact, keeping us grounded. Gravitation is what keeps us anchored to the Earth, preventing us from floating off into space. Planetary motion. The planets in our solar system orbit the Sun due to the Sun's strong gravitational pull. Gravitation acts as an invisible tether, keeping the planets in their orbits. Tides. The rhythmic rise and fall of ocean tides are caused by the gravitational pull of the Moon and the Sun on Earth's waters. Star formation. Gravitation plays a crucial role in the formation of stars and galaxies. Clouds of gas and dust in space are drawn together by gravity, eventually collapsing under their own weight to form stars. Gravitation is truly a fundamental force that shapes the universe at all scales. Section 9. Tides and orbits. The cosmic dance of gravity. The gravitational dance between celestial objects creates some of the most spectacular phenomena in the cosmos, including tides and orbits. Tides. The regular rise and fall of ocean tides are a direct result of the gravitational pull of the Moon and the Sun on Earth's waters. The Moon's gravity is the primary driver of tides because it's much closer to Earth than the Sun. The Moon's gravity pulls more strongly on the side of Earth that faces it, creating a bulge of water. A corresponding bulge occurs on the opposite side of Earth due to inertia. These bulges create high tides. Orbits. Planets, moons, and satellites stay in their orbits due to a balance between gravity and inertia. Inertia is the tendency of an object to resist changes in its motion. A planet in orbit is constantly being pulled towards the Sun by gravity, but its inertia keeps it moving forward. The result is a curved path or orbit around the Sun. Section 10. Gravitation, the key to space exploration. Understanding gravitation is crucial for space exploration. Rockets need to achieve escape velocity to leave Earth's gravity. Satellites balance speed and altitude to stay in orbit. Spacecraft use gravity assists to travel long distances. By harnessing gravitation, we can explore the cosmos. Section 11. Keep exploring. The universe of knowledge awaits. Gravitation, the invisible force that shapes our universe, is a captivating subject with endless wonders to explore. From the falling apple that inspired Newton to the intricate dance of planets and stars, gravitation is a testament to the elegance and complexity of the natural world. As we've discovered, gravitation is much more than just a force that keeps our feet on the ground. It's a fundamental force that governs the motion of celestial bodies, shapes galaxies, and influences the very fabric of space-time. I encourage you to continue your exploration of gravitation. Read books, watch documentaries, and never stop asking questions. The more you learn about gravitation, the more you'll appreciate the wonders of the universe we live in. Remember, science is a journey of discovery, and there's always more to learn.